Hi, in the previous videos we have seen convergence scenarios for martingales. We have seen what happens when the martingale is bounded in L1. We have seen what happens when the martingale is bounded in L2. The next big topics, the next big setup when we have martingale convergence will be the case of uniform integrability. In order to prepare for that, I need to leave martingales for a few videos, and I'm going to tell you about uniform integrability in general, which will be applied to martingales. I will start with a simple observation. Let x be in LP. So again, that means that the P's absolute moment is finite. And look at the events x mod larger than or equal to c for a fixed c number. C is a fixed non-random real number. Look at these events. I claim that these events are decreasing in C. As you increase C, well, C is not discrete, it's continuous, but that shouldn't worry anybody. So these events are decreasing in C. In other words, if I increase C, then these events are less and less possible to occur. In other words, if I have C1 smaller than C2, then x larger or equal to C1 is easier to achieve than x larger than or equal to C2. This is trivial. If x is larger than C2, then it's also larger than C1. So that's trivial. So these events are decreasing in C. That also means that if I look at the indicator of these events as numbers, these are 0, 1 numbers, these are also non-increasing in C. These are random numbers, these are random variables. These are non-increasing in C, right? For a particular omega, it might be 1 for a while, and then eventually, as I increase C, this condition will fail to hold, and in that case, this indicator will drop from 1 to 0 for any particular omega eventually. And also the limit of these events, the intersection of these events for all C is that x equals to infinity, which is the probability 0 event. So in fact, these events decreasing down to the empty set, at least the 0 probability set. Let me put it this way: decreasing down to a 0 probability event. Okay, with probability 1, x is not infinite, and therefore the intersection of these decreasing events, the limit of these decreasing events, is probability 0. Okay. Which means that this sequence of numbers is non-increasing in C, and this sequence of numbers converges almost surely to 0 as C goes to infinity. Okay, if C is getting larger and larger, then for any particular omega, this thing will go almost surely to 0. Okay. For an almost, the precise way of saying it is that on a probability 1 set of omegas, this thing is going to 0. All right. Now that means that if I now multiply the indicator with x to the p, then of course this thing is also going to 0 as C goes to infinity for any particular omega on a set 1. On a measure of 1 set of omegas, this thing will also go to 0 with C. And this whole business is bounded from above by the P norm without the indicator, because the indicator is 0, 1, and the mod of the P's power is non-negative. So this whole thing is bounded by the P's power of the absolute value of x. Okay, sorry, I said P norm, that's not right. There is no expectations yet. So it's the absolute value of on the P's power. That's a bound uniformly in C, which is of finite mean. Expectation of xp is finite by the assumption that x is in LP. So I have this sequence of numbers in C, sequence of random variables indexed by C, which is bounded uniformly by the p's moment of x, which is finite under the expectation. So therefore I can apply a dominated convergence theorem to tell me that expectation of xp times this indicator that x mod is larger or equal to c, this thing, the inner business has a limit in c that goes to 0. I have bound, and so if I take now the limit out from the expectation in c, I can do that, and by dominated convergence, or yes, dominated convergence with this domination term, I can conclude that this limit of 0 from inside the expectation can be taken out of the expectation, and for any given random variable, if I look at the expectation of x to the p under this event that x is at least c, then this will converge to 0. Okay, that was a short remark, and that's just to prepare you for the next definition, because now I want to define uniform integrability for you. Okay, so definition, a sequence of random variables xn of random variables is called p's power uniformly integrable p's power uniformly integrable if the following is true. So what am I going to do? I take the expectation of xn to the p on the event that xn is at least c. Okay, now I know that this thing, as c goes to infinity, goes to 0 for every single n. This is nothing special, it's just the green stuff repeated. So I'm going to take a limit as c goes to infinity, and I know that this thing is 0. However, the new thing, and it's very important, the new kind of addition to the green thing is that I'm going to look at the worst case scenario in n. So it happens uniformly in n that this limit is 0. Okay? Without the supremum, I would just be repeating myself with the green stuff. But the point is this supremum here, that you take the expectation of the p's power under the mode, you look at this event that xn mod is larger than or equal to c, you look at the largest of these in n. So you look at the worst case scenario in n, and then take a limit in c, it still goes to 0. So that's why it's called uniformly integrable, because this kind of integrability condition happens uniformly across the n's. And it's a property of this whole sequence of the xn's. So a sequence of random variables has this property. If this kind of integrability condition happens uniformly across n, in other case, it's allowed to take the worst case scenario and the limit still holds as 0.